Now, while subset selection is one way out, it has main drawback, namely you are throwing away some of the variables. So a more popular approach is what is called ridge regression. There are various ways to introduce the concept of ridge regression. We shall introduce it in the way it was originally introduced. So what we do is that we first look at this formula. The formula that we had to start with, beta hat is x prime x inverse x prime y, and the problem is that this x prime x is nearly singular, so inverting that is a numerically unstable thing. So what we do is a little ad hoc thing. We just rectify that by adding a little positive entity to each of the diagonal entries of x transpose x. Completely ad hoc, the way I am stating it. So you get x transpose x plus lambda I. So lambda is that positive entity. So I've written here lambda greater than equal to 0. And then you can invert that. So if you make lambda large enough, you are sure that this will be a non-singular matrix, a PD matrix. So you can safely invert. Whatever you get, you call that beta hat lambda. This is the ridge estimate of beta hat for the ridge parameter lambda. So this lambda is a tuning parameter. Now you might say, why should I do that? That just looks like a very ugly clause. Something was nearly singular, you just modified that. So how do I know that it has any good properties? Well, in order to see that, let's just make a little graph. So what I'm going to do is I'm going to draw a graph with lambda values in the x-axis and some characteristic of this thing in the y-axis. So that will show how good it is. Now we know there are two very standard ways by which you can compare. One is the variance and the other is squared bias. So let's try to look at the variance. The graph of the variance will look like this. Now why will it look like this? Pretty easy to see. As you make lambda very, very large, then obviously lambda is going to dominate. You will just not care about your x. So that is going to bring everything down to 0. Obviously variance will also go down to 0. So as lambda is made very large, it is going to overwhelm all the information present in the data, and you are going to get basically the constant estimate at 0. So your variance is going down towards 0 asymptotically. And the variance that you see up here for lambda equal to 0, that is the variance that you are going to see in case of your least square estimator. Incidentally, what am I showing here? Variance of what? By this I mean it is variance of some particular component of this. Suppose I am showing it for beta hat lambda 1. So I am showing it for one component. For each component you will get one such curve. So I am showing it one typical component. Now if the variance does not tell you the full story, you also need to have the bias squared. So let's see how the bias squared behaves. When lambda equal to 0, the bias we know is equal to 0 because least square estimator is unbiased. But as you put more and more value of lambda, the bias will gradually go up. So this is very natural thing, the so-called bias variance trade-off. When variance goes down, bias goes up. Now when you combine the two things, we know variance plus bias square, that gives you an important quantity called mean squared error, MAC. Let's see how that behaves. MAC will be sum of these two, so it will come down like this and then go up like this. So as variance goes towards 0, the MAC curve will asymptotically approach the bias curve. So this will be MAC curve for ridge regression. What will be the MAC curve for least square? That is basically when lambda is equal to 0. So that MAC curve will be just a flat thing because it is just same as this value. So whatever is your lambda, it does not use lambda at all. So if you are using least square, whatever is your lambda, least square is always same. Least square does not use that lambda. So this is the MAC for least square, and this is the MAC for the ridge regression estimator. So you can see ridge regression estimator is actually better in terms of MAC. Mean squared error is reduced. What it did was that it allowed a little bit of additional bias. It is biased, but at the expense of that extra bias, it had a great gain in terms of variance. The variance went down a lot. So you get something which is better than our usual least square estimator. And this will happen when you are working in a multicollinear setup. If it is not multicollinear, remember it is blue. So this variance itself will be pretty low. So this thing will not give you any appreciable benefit. So that is how ridge regression works. Of course, the question is, how do you really guess what particular value of lambda you should use? And there are various heuristics, etc. for that. But this is the main idea behind ridge regression. In the next video, we shall look at the same thing, but from a more modern approach, without presenting it just as an ad hoc way of fixing up things. Just out of the blue, I add lambda I. We shall look at it from a more modern and regularized viewpoint.